Welcome to lecture number 57, and we were actually discussing some elementary DC machines in the last couple of lectures. And recall that in my last lecture I told you about a simple type of DC generator where an aluminum disc is rotated at some given RPS of certain radius r, and there will be magnetic field from top to bottom penetrating the disc all over the surface of the disc. Then what happens is, if you consider a radial line, there will be induced voltage between the center and the perimeter of this disc, and the value of that voltage is given by this expression. Okay, this expression, this we got last time. So, it is directly proportional to B and radius square and RPS of the machine, rotation per second. Now, and also the polarity of the voltage will be this side plus, this side minus. And mind you that this induced voltage, that is along the radial lines the voltage exists, but along the direction of the theta, along the direction of the arc at any radius, there is no voltage difference between this point and this point, that does not exist, because they will be at equipotential points. If you draw a circle, that circle will become equipotential. Of course, the value of the potential increases if you as you travel from center towards the perimeter of the disc. So, this type of generator, of course, it is feasible, unlike your single conductor infinite length DC machine. This machine can be easily constructed, and this type of machine is given a name called homopolar machine, homopolar machine, DC homopolar machines. Now, how to collect this voltage? What you have to do is this: you have to take two brushes, fixed brushes, one is here and another at the center, somehow on the spindle. Suppose you connect the brass. Okay. This is the disc, you recall. This is the disc, this is the spindle. So, you connect just to give you idea, this is one brush, this is another brush. These two brushes are fixed and the disc will rotate, therefore, it will always touch the perimeter, the brush, fixed brush. So, one brush is there, another brush is there. This will be the negative brush, this will be the positive brush, and through these fixed brushes you will supply the load. Therefore, and the magnitude of the EMF generated is given by this. So, this is how you can generate DC voltage. In fact, this type of configurations or this type of DC generators are used when the magnetic field can be made very large, as in a superconducting coil will create this magnets whose strength will be very large. Okay. But anyway, this is for instruction, but for very large power at room temperature, this machine is not of mechanically very strong and things like that. Nonetheless, this also gives us some idea that how easily DC voltage can be generated, and we should not forget also that this type of machines can also be operated as a motor. So, as a generator, that homopolar machine homopolar DC machine, it can be also operated both as generator and also as motor. When it is operated as generator, we have seen it can be modeled as the generated voltage between the brushes, and maybe it is some resistance, effective resistance internal, and then your load resistance. This is the internal resistance and this is the generated voltage. And generated voltage we have seen it is proportional to this thing, that is pi n b r square. These two cancel, so pi n b r square. So, this is equal to pi n b r square. Let us use different notation. Here this is r 1, this r is the radius of the disc. And this r 1 is the internal resistance of the source, pi n b r square by something was there? No, pi n b r square, 2 cancels. So, pi n b r square, this will be the expression of the generated voltage. Okay. If you want to operate the same machine as a motor, then what you should do, as this is generator operation, for motoring operation what you should do is this. This is the disc, these are the two brushes. Okay. One is connected to the spindle, these are the two brushes. Here you connect a external supply, E supply voltage. If you connect a supply voltage like this with this polarity, then current will flow like this. It will come here at the center, it is connected to the disc, current will all flow radially. That is, if you look at the disc during motor operation, it will be the way I have drawn, it will be this and this. Currents will all flow radially. It will come here, then come here. Many parallel paths are there for current to flow, I. So, polarity of the applied voltage is such, it comes, suppose it was stationary initially, and let us assume that B is in this direction into the paper. Then you can apply the left hand rule B I L, and this machine will start running in the anti-clockwise direction. Left hand rule you have to apply, and it will in the anti-clockwise direction it will start running. And once again it will finally reach a steady speed when the applied torque, that is the electromagnetic torque developed is balanced by the opposite torque present on the system, okay, that is friction, whatever it is. But nonetheless, in this case, the moment it starts rotating, we must not forget each this radial lines become source of EMF of this magnitude pi n b r square. At t equal to 0, when it was beginning to start, you have switched on the supply with a switch at t equal to 0. Before that, it was stationary. You have closed the switch at t equal to 0, it was stationary, now it will start accelerating, electromagnetic torque will be produced, and if it can overcome the frictional torque present on the shaft, it will start moving. And finally, it will attain a certain speed when the opposing torque and the electromagnetic torque will be equal. Okay. Now, what is the direction of this force? If you calculate it, it is, we have seen B I L. Now, this segment, what will be the polarity of the voltage? In this case, polarity of the voltage will be, if you take an element here, it is moving with this V and this is B. So, B and V, this will be the polarity, that is the tip of this finger is towards the center and that will become plus. So, the polarity of the induced voltage will make this is plus, this is minus. It is correct, this is back EMF. So, it will try to oppose the inflow of current into the motor. The model in this case will be, there will be an back EMF with this polarity E B and this resistance R 1 in any case present, and then you have your E supply like this, E supply, and this is the current, and polarity of the voltage once again like linear motors, it will try to oppose the supply voltage. And when the things are running steadily, I can easily say that steadily drawing some current from the supply, I will say it is operating as a motor, and and delivering some mechanical power. How much is the mechanical power? Two ways it can be calculated. You calculate force, then multiply with velocity, whatever it is, integrate, or simply it will be the mechanical power will be E V into I. That will be also power supplied here is E supply into I, a power, certain power will be lost here, remaining power will be this one. So, you can then easily write that E supply will be equal to I into R 1 plus E B. Okay. Multiply with I both sides. So, you will get E supply into I E supply into I will be equal to I square into R 1 plus E B into I. This will be the thing. So, this is power drawn from the supply, a portion is lost as copper loss in R 1 and remaining power must be the mechanical power. Anyway, so it can operate both as a motor and generator mode, like our single conductor linear version of DC machine. Okay. So, after this idea of DC machines, and here no complications, only you require two fixed brushes, okay, to be touched, one at the perimeter, fixed brass, mind you, they are not moving. এটা ঠিক করতে হবে, fixed brass. So, this is the power balance equation of this simple DC motor, which has no complications whatsoever, so far its construction is concerned. Now, we will discuss about a formal large power DC machines, okay. And that is a DC machine with which will have a rotor, it will have a stator, and then it will be having a shaft, and it will run in a magnetic field, and there will be two terminals available to supply the rotor coils, there will be two terminals available to the stator coils, and if rotor carries current, rotor coils and stator coils both carry current, then they can produce some force and you get sustained rotation when the electromagnetic torque developed by the motor and the opposing torque present on the shaft of the machine becomes equal. So, before that it will look like that the DC machine has got I formal DC machines. DC machine will have a stator and a rotor. Okay. The rotor will be laminated iron circular plates with slots cut in it. And I will that is what I want to tell that the for example, this is the laminated plates of the coil where this is the armature winding of the machines. This is called the armature. Armature. So, there will be several such circular laminated plates, they will put one above the other and that will give you the length of the machine, and these are slot and teeth as usual, and there will be conductors placed on the slots in a following a particular logic, they will be placed and they will be connected. Okay. And the field structure of this machine will be, this is the rotor of the DC machine, rotor, where this is called armature and it has got slots and teeth and in which there will be copper conductors or coil will be placed. The stator part of the machine will look like this one, two projected poles, one on this side and the other on this side. Okay. And there will be on the stator. So, if I draw it in this in a small version, it will look like this. You have two projected poles on the stator, two projected poles on the stators, and there is this rotor business which has got slot and teeth all along as I have shown here, and these will carry conductors. On the stator, this is the stator iron and there will be coils here, which is simple coil. Stator coil is very simple, it will be like this. And if you pass some current through these coils, cross and dot like this, and these two coils are connected in say series, these two parts of the coils may be connected in series and you connect it to a DC supply, so that current flows in the stator coils, and then this will become a north pole, this will become a south pole produced by stator structure. So, I f is the field current. So, what I am telling, these two coils connected in series will ultimately give you two terminals available to you from the stator and they can be marked as F1 and F2, called the field coil terminals, field coil terminals. Got the point? And armature is slightly involved, that we will see, but the stator structure is made of iron and preferably solid iron, unlike induction machine stator, which must be also laminated. It is suppose a solid piece of iron and it has got a length, mind you. Similarly, the rotor will have a length like that. Okay. This conductor will run all along this, all the conductors in these slots. So, this is the stator structure, and stator is therefore can be represented by a simple coil, and I will pass some DC current IF like this, and these two coils are connected in series. F1, F2 is the ultimately two terminals coming out, and this is armature. Okay. But armature will be a bit complicated, we will come to that, and before that I will show you an actual DC machine armature, a small DC machine armature. This is what these slots and teeth are, slots and teeth, and there are several plates stacked together to give you the length of the machine. And in these slots you can see multi-turn coils are passing, and they will be connected in a particular fashion. And this part, which I will discuss extensively, why this is necessary, this is called the commutator segments. Okay? And it is this part which will help us to change the AC voltage generated in the coil to convert it to DC voltage. That we will take up later, but the idea is clear. So, this is rotor which will rotate in this shaft like this, and it will rotate in two stator magnetic field, one on this side north, another on this side south like this, and it will have a stator. So, stator part I have not brought, and there will be an air gap between this. This is the idea. I mean, you should have a physical idea how the machine looks like. That is fine. Now, before we start this DC machine, so stator is will give you projected poles like this. Stator is has projected poles, and to be excited with DC current with constant value of current called field current. Okay. Rotor will have rotor is also called armature, for a DC machine. Armature has several laminated circular plates, insulated from each other, from each other, like transformer from each other by a varnish coating or whatever it is, has several laminated circular plates insulated from each other to with number of teeth and slots. Okay. Now, before, so field winding, field coils, they are very simple. You simply have projected poles, around it you just suppose this is a projected pole like this, and you make the coil like that. And there is another pole, suppose here, and you have coils like this, here also and this is the structure of the stator poles. I have shown they are joined like this, and it will be a circular thing. So, it comes like this, red one are the coils, and this is the thickness, outer thickness of the iron of the stator. It will be like this joined. This is the stator iron, which is not laminated. The reason we will see. And these two coils, what you will do is this, these two coils you will connect in series, as I was telling, and you connect some, and these two terminals may be marked as F1 and F2, and your stator coils are ready. Now, to these stator coils, if you pass some, connect some resistance in say series, connect some in other color I show, connect some resistance and connect a DC source, it will send current like this, and the direction of the current will be like that. So that this will become a north pole, this will become a south pole. This is how stator poles will be created, and this is the. So, these two coils will be connected in general series to create a two pole structure like that. And then in the armature part is more crucial. The armature will be here like this with slot and teeth. This is armature, and here there will be coils placed in the slots following a certain grammar, certain logic, so that you can ultimately get DC voltage in it. So, we will continue with that. So, constructional features we are discussing of formal DC machines. Thank you.